In the previous lecture, we've discussed topological spaces, and in this part, we would like to construct a topology out from a distance function or a metric. So a metric is an abstraction of the Euclidean distance in Rn. So for the definition of a metric, consider a set X and a function d from X cross X to R. You can think of the first component as the starting point and the second component as the final or endpoint. Then this function d will be called a distance function or a metric if and only if for any 3 points x, y, z, and x, we have the following properties: m1, m2, and m3. The first one is what we call definiteness. So the distance from x to y will be 0 if and only if x is the same as y. The second property is symmetry, which tells us that the distance from x to y is the same as the distance from y to x. And finally, M3, the triangle inequality, tells us that the distance from x to y is less than or possibly equal to the distance from x to an intermediate point z plus the distance from that intermediate point to the second point y. And if we have a metric on a set X paired with the set X, then we shall call this pair a metric space. Again, if D is clear in the context, then we shall refer X as the metric space without referring to the metric itself. So these three properties, M1, M2, and M3, are in fact coincide with our intuition of what a distance should be. So to illustrate this, in the case of the Euclidean plane, definiteness means that your distance is 0 if and only if there is no movement, meaning the final and the terminal points are the same. Symmetry tells us that if you go from x to y, the distance that you have covered is the same as going from y to x on a straight line, of course. And finally, for the triangle inequality, going from x into y, that distance is less than or possibly equal if we move from x to z and then from z to y. And that's why, based on this picture here, this M3 is called the triangle inequality. In geometry, this tells us that the length of a side is less than the sum of the other lengths. Well, equality can hold if we have a degenerate triangle. Meaning, if, for instance, z is collinear with respect to the line segment determined by the points x and y. So in this way, the distance from x to z plus the distance from y to x is the same as the distance from x to y. Okay, well, on the definition, we say that a distance is a mapping from x cross x into the set of real numbers. Of course, we don't want to have a negative distance. Well, in most texts or in some texts, a metric is defined as a function from x cross x to the non-negative numbers. However, the three assumptions or the three properties M1, M2, and M3 in fact imply that the distance is non-negative. Well, to see this, let's start with the fact that the distance between x and itself is 0. Okay. Well, I can go to x if I move from x to y and then go back from y to x. So the first equality is definiteness, and the second inequality is due to the triangle inequality. And of course, by symmetry, I can interchange y and x in this case in order to have twice the distance from x to y. Okay, so dividing by 2, we can see that the distance between x and y is non-negative for all x and y in the set capital X. Okay, so the three properties here, M1, M2, and M3, indeed implies that a metric or a distance function is non-negative. Okay, so there is what we call an open ball. So an open ball with center X, an element of the metric space, with radius R, which is positive real number, is defined to be the set of all points in Y having distance which is less than R with respect to the center X. And this will be denoted by B sub D to emphasize the metric. The first component is the center, and the second component is the radius. So this definition of the open ball is motivated from the case of the Euclidean space. So if this is your X, then the open ball should be the interior of the disk centered at S with radius R. So you consider all points except at the boundary of that circle. Now, if we collect all the open balls centered at X having a positive radius, that will be denoted by script B sub D. The collection of open balls will form a base, a topological base to be precise. Well, to verify this, take any point in X. Take note that the center is always an element of the ball centered at X with radius 1, let's say. Okay. So that is the first condition for to be a topological base. The second one would be the following, and this is motivated from the Euclidean space. So if you have two open balls, okay, x1, x2, and a common point in x3, then you can take the radius. Okay, so let's repeat that one. So if I have an open ball with center x1 and radius r1, and another open ball x2 with radius r2. Okay, then you could take then an x3 in the intersection, then one could show that the open ball centered at x3 having the radius which is the smallest between the two radius. This is a subset of the ball x1 with radius r1 intersection with the ball having center at x2 and radius r2. Well, you can verify this inclusion by applying the triangle inequality. And the details are left for you to check. Now that we have a base, recall that once you have a topological base, you can generate a topology. And this topology will be denoted by T sub D. So this is called the metric topology. Therefore, the metric topology is nothing but the topology generated by the base B sub D consisting of the open balls. By definition, an open ball is open with respect to the metric topology. So the open ball centered at X with radius R is open with respect to the metric topology. Well, to see this, consider this open ball centered at X and then having a radius R. Pick a point Y in the open ball. Then we need to find an open ball that contains this point Y and lies entirely in the original ball centered at X with radius R. Well, what we can do is you can compute the distance between X and Y, and whatever the remaining distance in order to have R, we will take that as the distance or the radius of the ball, in this case colored in red. Meaning, if I choose delta to be R and minus the distance of X and Y, and we are guaranteed that this is positive because the distance between X and Y is less than R, because Y lies in this ball. Okay? Then the ball centered at Y, having radius delta, this one here, obviously contains X, contains Y, I should say, and this lies entirely in the original ball, having center X and radius R. Well, you could prove this as follows. So if you pick a point Z in the open ball centered at Y having radius delta, then if you compute the distance between Z or X, I should say, and Z by the triangle inequality, this is the distance between X and Y plus the distance between Y and Z. And this is less than the distance. Okay. So the first is unchanged. The second one is less than delta because Z lies in the ball centered at Y with radius delta. And by definition of delta, this is equal to R, which means that Z belongs to the open ball centered at X with radius R, which establishes this inclusion here. Okay. So again, open balls are open with respect to the topology. That's why they are called open balls. What is nice in metric spaces is that they are automatically Hausdorff. So as a consequence, all sequences can have at most one limit. So either the sequence is convergent or not. And if it is convergent, then the limit must be unique. Well, to prove that it is a Hausdorff space, a metric space is a Hausdorff space, pick two distinct points, x and y, then choose delta as half of the distance. We know that this delta is non-negative because x and y are distinct according to the definiteness of the metric. Then you can easily show that the ball centered at x having radius delta, as well as the ball having center y and radius delta are disjoint. So in this case, we have two open sets containing x and y that are disjoint. And that is basically the definition of the Hausdorff space. If given two distinct points, you can find two disjoint open sets that contain those points. Of course, from the previous remark, we know that open balls are open. So this furnishes the proof that metric spaces are indeed Hausdorff. Just for the sake of having an example, of course, the Euclidean space Rn with respect to this distance, which is the Euclidean distance, is a metric on Rn. Okay. And in analytic geometry, this is called the distance formula, in fact. And in, let's say, 2 or 3 dimensions, this can be derived from the Pythagorean theorem. Okay, so let me give the alternative formulations of convergence and a continuity of maps with respect to metric spaces. Since we have a base, topological base for the metric topology, the concept of convergence and continuity can be formulated in terms of open balls. For instance, in the case of convergence, so if I have a sequence x sub n converging to a point x, this is true if and only if for any epsilon greater than 0, I can find a natural number n. In general, this depends on the given epsilon, meaning a different epsilon will in general give you a different n. And in this case, the distance between the terms of the sequence and the limit is less than epsilon for any index greater than or equal to capital N. Well, you cannot see open balls here, but of course, this one here is equivalent in stating that x sub n should be in the open ball centered at x with radius epsilon. So therefore, all terms of the sequence, except for a finite number, should belong to the open ball centered at x with radius epsilon. So in the case of the Euclidean space, let's say, if you take epsilon to be small, then this ball is very small. Therefore, all terms but a finite number of the sequence will lie in that very small ball. Next, in terms of continuity, we have the following. So suppose we have a function f from X to Y. X and Y are metric spaces having metrics D sub X, D sub Y, respectively. Then continuity is equivalent to the following formulations. The first one is the familiar one, the epsilon and delta definition of continuity. This means that for any point in the domain, in every point epsilon, or every positive number epsilon, I can find the delta depending on X, the point X and the positive number epsilon, such that the distance between X and Y, if the distance between X and Y with respect to the metric of the domain is less than delta, then the distance between the corresponding images with respect to the metric of the codomain is less than epsilon. Well, in terms of open balls, you can say that if Y belongs to the open ball centered at X having radius delta, then the image should be an element of the open ball in Y having radius, which is the image of the point X, and radius epsilon, having center f of X and radius f sub epsilon. So here is the formulation of continuity in terms of the epsilon delta definition. And it can be, of course, equivalently formulated in terms of open balls. And finally, continuity is also equivalent to what we call a sequential continuity, which means that for any point X in the domain, and for every sequence that converges to that point, the sequence of images under F should converge to the image of the limit. In this way, we also say that a function between metric spaces is continuous if and only if it is continuous, if it is convergence preserving. Okay. Let's wait that. Okay, so if it is convergence preserving. Okay. So this is left as an exercise. So please verify these claims. And maybe you have proved this probably in a course on topology. Okay, paramount to the concept of metric spaces is what we call completeness. So before we define what do we mean by a complete metric space, let us define what do we mean by a Cauchy sequence. So a sequence is said to be Cauchy if for every positive number epsilon, no matter how small, you can find a positive integer n depending on epsilon, such that the distance between the terms of the sequences having indices greater than or equal to n is less than that given epsilon. This means that after some finite number of indices, the distances between the points of the sequence or the terms of the sequence can be made arbitrarily small. Well, in general, if epsilon is very small, then you might need to take a larger value of the integer n. Okay. One can show that convergent sequences are Cauchy. However, in general, Cauchy sequences may not converge to an element of the metric space. However, if it happens that every Cauchy sequence in a metric space converges to an element of that space, then it is said to be complete. Again, a complete metric space is a metric space wherein any Cauchy sequence will converge to an element of the metric space. Before going to the significance of completeness, let us prove the following theorem. So a closed subset of a complete metric space is also complete. So let us look at the proof of this simple fact. Okay, so let's start with the metric space X with metric D. And a subset, let's say A of X, which is closed. So here, by closed, we mean with respect to the metric topology. Now, in order to show that A is also a complete metric space, of course, we need to define what is the metric of A. And this will be the restriction metric. In other words, we will define a metric on A by following whatever the distance of X and Y with respect to this original metric in X. Okay. X, Y, and A. Then, one can show that this is indeed a metric on the subset A. This means that this pair is a metric space. Well, if you want to prove the three properties, that is the definiteness, symmetry, and the triangle inequality of this metric on A, you just need to apply the corresponding properties of the original metric D on X. In other words, those properties of a metric D are inherited by the restriction metric D sub A. Okay, so to prove completeness, let us take the Cauchy sequence in A. Okay. Therefore, it is also Cauchy. It's also Cauchy in X. Because, take note here, they are the same metric. The definition is the same. The main difference is, of course, the domain where these metrics are defined. Okay, knowing that X is complete, thus we can find a limit in the complete metric space X wherein Xn converges to X. Of course, with respect to the topology of the metric space X. Now, using the fact that A is closed, since A is closed, one can show that closed sets contain all limit points, all its limit points. Therefore, X must be in A, and the sequence also converges with respect to the metric topology on A, due to the fact that, of course, again, the definition or the values of the metrics D sub A and D are the same. So therefore, we have shown that every Cauchy sequence in A converges to an element in A. And by definition, this means that A is a complete metric space. Okay. So again, a closed subset of a complete metric space is complete with respect to the restriction metric. One of the classical application of completeness is what we call the Banach contraction principle. So let us consider a complete metric space X comma D and a function from X into itself. And this function is said to be a contraction, meaning there exists a row between 0 to 1 such that the distance between the images, say, of X and Y is less than or equal to the distance between the corresponding points X and Y times the constant row. Well, one point is that this is called a contraction because if you take the distance of the images, it will be less than the distance of the corresponding points where the function is evaluated. Because take note here that row is less than 1. So the distance of the images is less than the distance of the pre-images. Second, a contraction is also what we call a Lipschitz function. And in this case, the Lipschitz constant is the number row. And in this way, all contractions are continuous. So for instance, in the epsilon delta definition, if you have an epsilon, then you can choose delta, let's say, to be epsilon over the constant row. Okay, so if we have a complete metric space and a contraction from this metric space into itself, then there exists a unique X star in the metric space such that the function value of that point X star is unchanged. Such a point is called a fixed point of F. Well, let us look at the proof of this theorem. So if you are familiar with the contraction principle, the proof follows the Picard, what we call the Picard iteration. So the first step is to choose any point in the domain and iteratively define the consecutive points of the sequence to be the function value under F of the previous term. So what we claim here is that this sequence generated in this way is in fact a Cauchy sequence. Okay, so first let us look at the distance between x1 or x2 and x1. By definition, x2 is the image of x1, while x1 is the image of x sub 0. Now I apply the fact that D is a contraction, so therefore this is less than rho times the distance of the points x1 and x0. Okay, Now, let us go quickly. One can show by induction that the distance between xn plus 1 and xn, if you want to go until the distance of the two initial points x1, x0, you need to repeat this process n times. In other words, you need to apply the fact that the function is a contraction n times. Thereby, you will have a constant rho sub n in this inequality. Knowing this, or having an estimate between distances of consecutive terms of the sequence, we can now estimate the distance between any two points of the sequence. So suppose, without loss of generality, let us suppose that m is larger than n and n is greater than or equal to 1. Well, what we know is that we can estimate the distance between consecutive points. So here, we will apply the triangle inequality several times and put intermediate points. So here, we put at xm minus 1. Then you have xm minus 2 until you reach the index n. Okay. We did this because we know that the distance between consecutive points can be estimated by this time. Okay. So here, the first one is less than or equal to rho raised to m minus 1 times the distance between x1 and x0 plus rho raised to m minus 2 times the distance between x1 and x0 up to the distance between, or rho raised to n times the distance between x1 and x0. Okay, so there's a common factor that you can notice here. By factoring the distance between x1 and x0, you will get the following expression. And let us move this to the left. So you could see immediately that this is a geometric sequence. And you can estimate the sum of this geometric sequence by rho raised to n over 1 minus rho times the distance between x1 and x0. Okay. And from this inequality, take note that this goes to 0 as m and n goes to infinity. Okay. And based on this, we can now conclude that xn is a Cauchy sequence in X. And by completeness, this implies that there exists an X, or let us call that X star, such that xn converges to X star in X. We claim that this is a fixed point of the function f. First, if you apply the continuity of f, a while ago, we said that a continuous function on a metric space is convergence preserving. And take note that f is a contraction, therefore it is Lipschitz continuous, in particular continuous. The image of the sequence will converge to the image of the limit x star. So this is by continuity. By definition, this is x sub n minus 1. And as n goes to infinity, of course, this will also converge to x star. In metric spaces, we know that limits are unique because, as we said a while ago, metric spaces are Hausdorff. So the by uniqueness of limits, f of x star should be x star. So this proves the existence of a fixed point. So that would be our first step. Existence. And let us move this one above. Okay. So now that we have the existence of a fixed point, the second step would be the uniqueness. As usual, to prove uniqueness, you consider two fixed points. So suppose I have a fixed point x star and possibly another fixed point, say y star. Our aim is to show that x star must be the same as y star. Well, we can look at the distance between x star and y star. Since these are fixed points of f, x star is the same as f of x star, and y star is the same as f of y star. And the fact that f is a contraction, this implies that the distance between the images is less than rho times the distance of the inverse images. X star, X star. Okay. Now, since rho is positive and strictly less than 1, this is possible only when the distance is 0. Okay. Take note that if the distance is strictly positive, then you will get a contradiction because the right-hand side would be strictly less than the left-hand side. Okay. By definiteness of the metric D, we can now conclude that x star is the same as y star. So if there are two fixed points, then in fact these fixed points are the same, and that proves uniqueness. Okay. So that's the contraction, Banach contraction principle. And it's also called the Banach fixed point theorem. Well, this theorem can be used in, let's say, convergence analysis of root finding problems in numerical analysis, for instance. It can be also used in proving the existence and uniqueness of solutions of ordinary differential equations or systems of ordinary differential equations. And an example or the proof of that theorem, which is called the Picard-Lindelof or the Cauchy-Lipschitz theorem, will be provided in the lecture notes. So those who are interested in the application of the Banach contraction principle in the problem of existence and uniqueness of system of ordinary differential equations, you might want to read the course notes. So what if a metric space is not complete? Can we enlarge that metric space in order for it to be complete? This is in fact the content of the following theorem, and it also gives how to construct the completion when we look at the proof later. So consider a metric space XD. Then we can find a complete metric space X bar D bar and a map J from X to X bar, wherein this J satisfies the following properties A and B. The first one is that this map J is an isometry. In other words, the distance of the images with respect to the metric D bar is equal to the distance of the inverse images. This is also called a distance preserving map. So the distance is preserved even though you apply the mapping J on the points X and Y. And moreover, the image of this map, J of X, is dense in X bar. So that's why the notation for this metric space for the codomain is denoted by A bar. Because if you take the closure of the image, it would be X bar. In this way, this is called the completion of your metric space XD. Okay. So before looking at the proof, let us consider the following remark. Okay, an isometry is automatically an injective map. Well, to see this, you could check by definition. Okay. So if the distance between the 2 points Jx and Jy is 0, so first, if J of X is equal to J of Y, then of course, according to the first property of a metric, the distance must be 0. But by the fact that J is an isometry, this would imply that the distance between X and Y is 0. Hence, X must be equal to Y. And this shows that, in fact, J is injective or a one-to-one mapping. So in this case, since J is injective, we can identify uniquely elements of the domain and the image. Since if you consider the restriction of the codomain with respect to the image, then the map J from X to the image J of X would be a bijection. So there is a one-to-one correspondence between elements of X and elements of the image J of X. So in this way, we can consider X as a subset of the completion X bar. Of course, here subset means actually that X has been identified with the image set, okay? And this image set is of course a subset of the codomain X bar. So this identification means that X is identified with the image set or the image of that point X with respect to J. And this identification is well defined because the map is a bijective function. So with that, let us look at the proof of the theorem. So if you are familiar with the proof of constructing the real numbers from the rationals, then the proof is technically identical. So for this proof, we will divide it in several steps. The first step is the definition of the extension. By this extension, or I mean completion, is denoted by X bar. Okay. So first, let us collect all Cauchy sequences in X. So this is the set of all Cauchy sequences in X. And on this collection, we will define a relation. Two Cauchy sequences are related if and only if the distance between the corresponding terms goes to 0. Okay, this relation satisfies the following properties. First, Xn is related to itself, which follows immediately from the definiteness of the metric. Second, if Xn is related to Yn, then we can interchange these two here by symmetry and see that Yn is related to Xn. And finally, if Xn is related to Yn and Yn is related to Zn, then we can say that Xn is related to Zn by applying the triangle inequality. Okay. These properties implies that we have an equivalence relation on C. Okay, now that we know that this is an equivalence relation on C, we form or we define X bar to be the corresponding quotient space. Or in some texts, this is called a factor space. So this is, by definition, the collection of all equivalence classes where the equivalence class uh, containing or determined by the Cauchy sequence xn is by definition the set of all Cauchy sequences yn that are related to xn. Okay. So this will be the definition of our completion. It is the equivalence classes of Cauchy sequences with respect to the relation defined in this manner. Cauchy sequences are related if and only if the distance between the corresponding terms tend to 0. Okay, now that we have constructed the set X bar, we now construct the metric. And this would be the second step of the proof. Okay, so consider a function d bar from x bar cross x bar into R as follows. So the distance between two equivalence classes of Cauchy sequences is defined by the limit of the distance with respect to the original metric D of the terms of the representatives xn, yn. So before showing that this is indeed a metric, we need to show that it is well defined. Okay, well, to prove that it is well defined, we need to establish several things. First, we need to establish the existence of the limit. Okay, so by applying the triangle inequality, we can compute the distance between xn and yn. So here, let us introduce two intermediate points, one with xm and then one with ym. So this is done by the triangle inequality, M3. Okay, and this implies that by subtracting the distance between xm and ym both sides, we will have this inequality. Okay, The next trick is to interchange n and m. Okay, this should be yn. Okay, if we interchange n and m, we would get the following inequality. This is yn. And now I apply symmetry. So this would be the distance between yn and ym as well. Okay. So here, this should be m and this should be n. But we applied symmetry so that we can interchange the two. Okay. So let's say this is inequality 1 and inequality 2. So 1, when you combine 1 and 2, then you get the following estimate. So the absolute value of the difference of the distances between xn, yn, and that of xm and ym is less than or equal to the following sum. And take note that xn and yn are Cauchy sequences. So this tends to 0 as m and n tends to infinity. Okay, so what is the significance of this? This implies that the sequence of distances is Cauchy in R. So therefore, by completeness of R, the limit as n goes to infinity of this Cauchy sequence exists. Okay, so that's the first part in proving that it is well defined. The second portion is the independence with respect to the representative. Take note that an equivalence class here contains a collection of Cauchy sequences. And what if I choose a different representative of the equivalence class? We should get the same value for D bar to be well defined. Okay, so let us see that here. So independence with respect to the chosen representative of the equivalence class. Okay, so let us take representatives denoted by prime of the two equivalence classes determined by the Cauchy sequence xn and the Cauchy sequence yn. Okay, then if we apply the triangle inequality M3 and doing a similar process as before, we introduce intermediate points. Okay, here we put xn prime and compare the distance between xn prime and yn prime. Then you'll have the distance between yn prime and yn. Okay, now if we pass to the limit n to infinity, what we would get is the following. By definition, okay, this means that xn prime is related to xn. So this means that this goes to 0 as n goes to infinity. Okay. Similarly, yn prime is related to yn, and this will go to 0. And we end up with the following inequality. So the first one, by definition of d bar, is the distance between the equivalence class determined by the Cauchy sequence xn and the equivalence class determined by the Cauchy sequence yn. Since the first and third terms on the right-hand side tends to 0 as n goes to infinity, the second, so term as n goes to infinity is the limit of xn prime, the equivalence class determined by xn prime, and the equivalence class determined by yn prime. Okay. So let's move this a bit. Okay. Now we do the same trick by symmetry of the argument. We get the other inequality. In other words, you put a prime on the left-hand side, and on the right-hand side, you introduce the intermediate points xn and yn. So the details are left to you to check. So therefore, if I choose a different representative of the equivalence classes, I get the same value of the metric d bar. In other words, the definition of d bar does not depend on the chosen representative for the equivalence class. Okay. So this is just the definition of the extended metric d bar. We have not yet verified that this is indeed a metric. Okay. So the next step that we would like to show is that the pair x bar d bar is indeed a metric space. Okay. The symmetry, or let's say, call that M2. M2 and M3. Okay. For the extended metric d bar, here I'm saying that it is already a metric, okay, or for the function d bar, follows from those of the metric d, meaning the symmetry and triangular inequality and the properties of limits of sequences for the set of real numbers. So they are inherited. So the properties of symmetry and triangular inequality is inherited by d bar. And you can check that immediately. Well, for definiteness, we only need to prove that if the distance between two equivalence classes of Cauchy sequences is 0, then these two equivalence classes should be the same. Okay. By definition, this means that the limit as n goes to infinity of the distance sets of the terms of the sequences is 0. But recall that this is actually the definition of the equivalence relation tilde. And therefore, take note that two equivalence classes are the same if the corresponding representatives are equivalent. And in fact, this is also valid in the other direction. Therefore, D bar is symmetric on X bar. Now that we have constructed the metric space, the next step is to construct the mapping from X to X bar. And that would be the next step. So that is now the third step. Step 3. Construction of the map G. Okay. So for the definition, let us define J as follows. Okay. So J of X is the equivalence class determined by the constant sequence. So this X is in the domain capital X. So in other words, X sub n is equal to X for any positive integer n. Well, to see that J is an isometry, looking at the distance between the corresponding images. So by definition of the map J, again, this is the equivalence class determined by the constant sequence X and the equivalence class determined by the constant sequence Y. Since the sequences are constant, take note by definition, this is the limit of the distances of the terms of the sequence. But since this is constant, you end up with the distance between X and Y respectively. So therefore, J is distance preserving or an isometry. Okay, so this proves the fact that J is an isometry, the first property. The second property is that we need to prove the density of J, of X in X bar. So to do that, let us pick an element of X bar. So that's an equivalence class of the Cauchy sequence. Now, given a positive epsilon, we can find an n in such a way that the distance between x sub k and x sub m is less than this positive number epsilon over 2 for all k and m greater than or equal to n. And why is that? Since the sequence x sub n is Cauchy. Now, if we take, let's say, k to be a specific number, say n, okay, by definition of d bar, so the distance of the constant Cauchy sequence, equivalence class determined by the constant sequence x sub capital N, and the Cauchy sequence x sub n. Okay, so by definition of d bar, this is the limit as n goes to infinity of the distance of x sub capital N, x sub n, okay, and this is less than the limit superior as m goes to infinity of x sub capital N, x sub m, and if you look at this inequality here, if you pass m to infinity and choose k to be n, you end up with an inequality less than or equal to epsilon, which is of course less than epsilon. Thus, the distance between xn, the Cauchy sequence are determined by the constant sequence xn, and the point that we have chosen in x bar is less than epsilon. The important thing here is that this one is equal to, by definition, j of x sub capital N. And this is, of course, obviously an image of the image set. It is an element of the image set j of x. Okay. So this means that any point x bar in x bar, there's a point that can be made arbitrarily. There's a point in the image set that can be made arbitrarily close to that point in x bar. And one could show that in the case of metric space, that would imply density. So we can now conclude that Jx is dense in x bar. So now for the final step of the proof, we need to show completeness. Of course, of the pair x bar d bar. Well, this is the generic or the basic step in proving completeness. So the first step is that you want to construct the limit. Second, we need to show that this, or candidate limit to be precise, show that this candidate limit lies in the space so is in the space And then finally, show or verify convergence of the Cauchy sequence to the candidate limit. Okay, so this is the generic step in establishing completeness of a metric space. Again, if you pick an arbitrary Cauchy sequence A, you construct a candidate limit. B, you show that the candidate limit lies in the space. And finally, verify that indeed the Cauchy sequence will converge to the constructed candidate limit. Okay, so let us apply this in establishing the completeness of the metric space X bar, E bar. So let's start with a Cauchy sequence of equivalence classes. So let us denote that by a K. Okay. And to be precise of the notation, okay, you consider the following. So we have a sequence of Cauchy sequences. Here, the Cauchy sequence is indexed by K. So again, we consider a Cauchy sequence of equivalence classes of Cauchy sequences in X. You can pause this video so that you can have an intuition of these sequences. Now that you have a rough idea, by definition of a Cauchy sequence, this means that for every positive epsilon, I can find a number, let's say R, depending on epsilon, in such a way that the distance between the terms of the Cauchy sequence, call it X and J, and X and K, this is less than epsilon, and let's say that this is less than epsilon over 2. For all J and L or K, okay, so let us use an L here. For any J and L less greater than or equal to R. Okay, so let us point out that this one here is in fact, by definition, the limit as n tends to infinity of the distance of X and J and X and L. Okay. For the next step, take note that for each K, by the definition of X bar, X and K, well, with respect to the index n, is Cauchy in X. So this means that there exists an nk, and let us choose this nk large enough, meaning greater than or equal to k, such that the distance, here k is fixed, okay, the distance between these 2 points is less than epsilon, and we take the positive epsilon to be 1 over k. As long as the indices n and m is greater than or equal to n sub k. Now, based on this, we can now construct the candidate limit. And that would be the sequence yk, which has the following components. So we just take the smallest possible integer in such a way that this is the above inequality or the previous inequality is valid. Okay, by definition, you could see immediately that the distance between x and k, if I choose m to be nk, then I should get yk here. This is less than 1 over k for all n greater than or equal to n sub k. So that furnishes a in the above claim or in the above process. So we have constructed the candidate limit. So next, we would like to show that the constructed candidate limit is indeed in x bar. Okay, first, if you apply the triangle inequality, which we denoted as M3, let us look at the distance between ym, yn. Okay. For definiteness, let's say n is larger than m or possibly equal. And these are both greater than r. Then we need to introduce intermediate points. Okay. So it's less than the distance. By definition of ym, this is x and m raised superscript m. And we need to put an index, let's say L, okay, in this case, n, or I should say m, using the same point, but now here we will use a different superscript n. And if you use the definition of yn, that is x sub n raised to or superscript n. Okay. So take note here that we use the fact that this is what? Scholar.1, this one is the same as this. And yn is the same as this. So that is the triangle inequality. Now, we could use this inequality here, or this one, I should say. So if we have the same superscript, as long as the indices here is greater than nk, okay. Now we are guaranteed that we can apply that as long as the intermediate point that we have introduced, having the subscript L, is larger than, let's say, n sub n and n sub n. So let us name this as star. Okay. So this is strictly less than. The first term would be 1 over m. That's the superscript. The second term will be the same. And the third term is less than 1 over n. Okay. Now that we have this, if we pass L to infinity, okay, and we going back to the definition a while ago. So let us go back to the very beginning. Or I should say this one here, okay? Let's call this double star. So take note, as we let n tend to infinity, you would get a limit that is less than epsilon over 2. Okay. So with that, so using double star, if I take the limit, well, we don't know yet if the limit exists. So let us take the limit superior as n, m and n goes to infinity of dym and dyn. This is less than or equal to, okay, this one goes to 0, this one goes to 0, and we have less than epsilon over 2. Okay, well, to be precise, to be more clear, you pass L to infinity first, okay, and take limit superior, or the limit supremum, as m and n tends to infinity. Okay. Here you see we need to use the double star. Okay. Now, since epsilon is arbitrary, okay, we can take or we can pass epsilon to 0 in order to get that the limit superior as m and n, okay, of the distance between yn and ym is less than or equal to 0. As we know, the limit superior is less than the limit inferior. And since distances is bounded from below by 0, this is non-negative. Okay, so it will be squeezed, meaning the limit inferior and the limit superior should coincide, and in fact, the limit must be 0. So therefore, the limit as m and n tends to infinity of dym and dyn, and this should be ym is equal to 0. This means that, of course, by definition, yn is Cauchy in X. Hence, we can construct the associated equivalence class. And obviously, by definition of X bar, this is in the factor space X bar. And this is in fact the part B that we are mentioning, or that we have mentioned a while ago. That is let us change the color there. That is the equivalence class or the candidate limit is in X bar. Okay. Finally, for part C, we need to verify that indeed this constructed candidate limit converges is the limit of the original Cauchy sequence. Well, that follows immediately from the definition of D bar. So let us look at the distance of the terms of the Cauchy sequence with the candidate limit. Okay. By definition of D bar, this is the limit as n goes to infinity of x and k and yn. Okay. We introduce 2 points here. So by the triangle inequality, dx and k, and then yk plus dyk yn. And this is less than the limit. But since we are not yet guaranteed if the limit exists, let us take this limit superior in this case. Okay. Now, the first one, first limit superior is less than 1 over k. By, so we need to check above, by this property here. Okay. And similarly, for the second part, including, of course, the limit superior, this one is less than 1 over k plus epsilon over 2. And where is that? Or I should say less than epsilon. This is less than epsilon over 2. Where this inequality here. And I think there should be plus 1 over k in this case. You need to see that one. Okay. So in this case, you need to apply, in fact, this one. You interchange k, m here by k. You pass to infinity. This one will go to 0. And this one is less than epsilon over 2. And you end up with that inequality. Okay. So that would be 1 over k plus epsilon over 2. So combining the estimates, we will have, this is 2 over k plus epsilon over 2. Okay. Now, if you pass k to infinity, and then you pass epsilon to 0, you will obtain that this one here, let's copy that one and put it here. Oops. Okay, so putting that limit, this one goes to 0, as k goes to 0. So therefore, the original Cauchy sequence converges to the candidate limit that we have. And this proves the completeness and therefore the proof of the theorem. Okay, that was a long proof. So to summarize, let us go back to the statement of the theorem. So given a metric space, you can find, roughly speaking, a larger metric space that is complete and will contain that metric space. Moreover, it can be shown that this metric space, the completion of the metric space, is unique up to a bijection. And that's it for metric spaces. The next lecture will be on semi-norm and norm spaces. Thank you and see you there.